We have been talking about the SN2 reaction, and last time, in the last couple of minutes, I showed you something that you didn't want to see, but you saw it anyway. And it's related to what the LUMO of an alkyl halide like this molecule really is. You're used to now looking at a molecule like this and saying, oh yeah, the LUMO is the carbon-bromine sigma star. I've copied these two images over from the Spartan program. They're side by side and about the same size so that you can see where everything is. But if we were to draw sort of a stick structure, this is what it would look like. Here is the carbon-bromine bond angled slightly towards you. Here are carbon-hydrogen bonds angled slightly away from you and 180 degrees away from the carbon-bromine bond. All right. And then here is the calculated image of what the LUMO is. And it looks like the carbon-bromine sigma star. Here is the node in between the two nuclei. Okay, it doesn't like what I'm doing there. I don't know what's going on. All right, I won't draw on the structure. Yes, I will. There it is. Anyway, there's the node in between the two nuclei. You can see the shift in wave function. It doesn't like to do, this is really frustrating. I'm trying to use the laser pointer function. Oh well. You can see a switch in wave function sign as you go from one side of the node to the other nodes at the nuclei that are typical of these orbitals. So that looks like a basic carbon-hydrogen sigma star. What's unusual here and what's new is that there is some LUMO on these adjacent hydrogens, and we need to talk about that. That's been going on all along, but I have deliberately concealed it from you because I didn't want to worry you before we needed to, but now it's time. So let's talk about what's going on, and before we do that, we need some tools to describe, just some nomenclature type tools to describe the relationship of groups relative to each other. This carbon that contains the bromine group, it's adjacent to the bromine, we're going to call it the alpha carbon. And then these two hydrogens, which are adjacent to the alpha carbon, we're going to give the Greek letter delta, alpha, beta. Sorry, did I say delta? I was totally saying beta in my head when delta came out of my mouth. I'm sorry about that. So the carbon that's adjacent to the alpha carbon we're going to call beta. Now, you look at this molecule, the two beta carbons are identical, so we're only going to worry about one of them in our discussion, but what goes for one goes for the other. We need to talk about why then the LUMO is on, can I really not draw on that structure? Shoot, that's really annoying. Why the LUMO is not only on the alpha carbon, where you would expect it to be, but why it's also on the beta hydrogen. So this has to do with a concept called hyperconjugation. It's something that I think your study guide mentioned previously, but we didn't say a lot about, mostly because it wasn't worth the trouble at that time. It is now. So what is hyperconjugation? This is when a filled orbital overlaps with an adjacent empty orbital. This is a concept sort of from valence bond theory. It's not a concept that's necessary in molecular orbital theory, but it's one that we'll use because it allows us to think about how orbitals spread out onto adjacent atoms. So a filled orbital overlaps with an adjacent empty orbital in the same molecule. And in general, what are the filled orbitals that we're talking about? Need more space. This could be a lone pair. It could be a pi bond. It could be a sigma bond. And what could the empty orbital be? Well, it could sort of be anything. It could be, I am so tired of that image, I'm deleting it. There we go. Goodbye. It could be, why can I not write there? There's some residual weirdness. That's obnoxious. Obnoxious residual weirdness. It could be an empty p orbital, it could be a pi star, it could be a sigma star. Now, we've talked about overlapping of filled orbitals and empty orbitals before. In fact, that's actually what's going on when we have the nucleophile attack an electrophile, right? A filled orbital on the nucleophile, the HOMO, is attacking the empty orbital on the electrophile, the LUMO. But we're talking about a filled orbital overlapping with an empty adjacent orbital, all in the same molecule. And when this happens, there are a few consequences. First, the filled orbital spreads out. And because of that, that delocalization, how do I spell delocalization? That delocalization is stabilizing. The second thing that happens is the empty orbital spreads out too. And we can draw this happening. So let's envision that going on here. What's the filled orbital and what's the empty orbital? Well, as we discussed, and if you'll allow me, I think for the purposes of this discussion, I want to draw this molecule just a little bit differently. Maybe what I'm going to do here will make it a little bit clearer. I'm going to go ahead and draw the carbon-bromine bond in the plane of the page. I don't think this makes a huge difference. And there's another carbon-hydrogen bond here, which I'm not going to show. All right, so the sigma star, the empty orbital, will draw a node in between the two atoms here, smaller lobes here facing the node, and then larger lobes here pointing away from the space between the two nuclei. We won't use the same colors as were in that image that I copied over from the program, but here we go. All right, so that's the empty orbital. That's the empty carbon-bromine sigma star. Now, what's the filled orbital? We're going to only draw one of them, but what's true for one beta hydrogen that I'll show you is true for the other. The filled orbital is the carbon-hydrogen sigma bonding orbital. So we can draw that like this. Okay. So this one has electrons in it. The filled carbon-hydrogen sigma bonding orbital. You comfortable with where those orbitals are? What they look like? Okay. Now, the idea of a filled orbital and an empty orbital on adjacent atoms sort of spreading out into each other is unusual, but it is something that can occur. If you remember our energy diagrams, when we were thinking about orbitals and how far apart they are in energy, if sort of around here is where you would expect a non-bonding atomic orbital to be, a sigma bonding orbital would be quite low in energy. And of course it's filled because it's got electrons in it. And then an empty anti-bonding orbital, like the carbon-bromine sigma star, would be quite high in energy. One's a bonding orbital, one's an anti-bonding orbital. Okay. Now, if we're going to have a filled orbital mix and overlap with an empty orbital, we've done that before a ton of times. That was the first thing we ever did in this class, where we had two 1s orbitals, two from two hydrogens interact to form a bonding orbital and an anti-bonding orbital, right? What we're going to do here is very similar. We're going to mix the filled bonding orbital with the empty anti-bonding orbital, and we're going to get two new orbitals out, all right? We're going to get one that's just a little bit lower in energy than the carbon-hydrogen bonding orbital, and the other that's just a little bit higher in energy than the sigma star antibonding orbital. We're not going to worry about it too much because these two orbitals are so far apart in energy that the mixing they do is going to be very, very small and very minor. Back before, when we did hydrogen, we mixed two 1s orbitals together and we got a new sigma bonding orbital out, and that sigma bonding orbital was about 105 kilocalories per mole lower in energy than the starting orbitals we began with. In contrast, because our filled bonding orbital and empty antibonding orbital are so far apart in energy, when we mix them, we're not going to get a big kick in energy out. In fact, we're going to get maybe 3 or 4 kilocalories per mole. So this is one reason why it's called hyperconjugation rather than bonding. It's like a stabilizing effect, but it's worth way less than a full bond is worth. So what I'm saying is when we mix the two orbitals together, we're going to get one that's modestly lower in energy than the bonding orbital, and then we're going to get a second that's modestly higher in energy than the antibonding orbital. I'll use a dotted line to sort of communicate what's happening here. All right, this is going to be the plus combination, the sigma CH plus, the sigma star CBR. This is going to be the minus combination, the sigma CH minus the sigma star CBR. Right, so what I'm showing you here is that you can mix a bonding orbital with an anti-bonding orbital. You get two new orbitals out. You get one that's a plus combination and one that's the minus combination. I'm going to draw for you what these two combinations look like. But remember that because the mixing of the two orbitals is small, it's a small effect, this one is going to look mostly like a sigma bonding orbital, only it's going to be spread out a little bit onto the beta hydrogen. And this one is going to look mostly like a sigma antibonding orbital, only it's also going to be spread out a little bit onto the beta hydrogen. Okay? So just imagine, I'm going to sort of copy, no, we'll redraw it. What does the plus combination look like? Well, here we go. Carry on, whatever you need. We don't need to evacuate, do we? No, we're okay. All right. All right. So the filled bonding orbital is going to look mostly like a carbon-hydrogen sigma bond, only it's going to be spread out a little bit onto the adjacent carbon bromine area. All right, folks, I dare you all to pay attention to me instead of the men with the ladders. Okay. Do you see how this is mostly a carbon-hydrogen bonding orbital, but there's a little bit of the sigma star in there? And if you look at it from a certain perspective, what we've drawn here almost would be better drawn like this. It's almost as if the carbon-hydrogen sigma bonding orbital is spreading out and you've got partial pi bond character there. Okay? It's almost like there's partially a double bond. And in fact, this is where the term hyperconjugation really comes from. All right. Over here, for the anti-bonding combination, this is going to look mostly like the sigma star. only there's going to be a little bit on the adjacent hydrogen. But because it's the minus combination, the lobes are going to be sort of out of phase, out of wave function sign. All right. So what this means is the electrons that are in the carbon-hydrogen bond are spread out a little bit onto the adjacent beta proton. And the empty orbital, the empty antibonding orbital, is spread out onto the adjacent beta proton as well. Now, questions that people have about hyperconjugation. They say, I thought in the past you told me that if we put electrons in an antibonding orbital, we break the bond. How does that work? And the answer is, we're not fully dumping an extra pair of electrons into an antibonding orbital. Actually, we're just mixing the orbital, the antibonding orbital with the bonding orbital. The bonding electrons get to move a little bit lower in energy. The antibonding orbital gets to move a little higher in energy. We don't care because it's empty. All right, questions so far? Yeah, no, we're pointing. Sorry, I thought we were waiting. That's okay, you can point. Yes?
So what was the sigma star antibonding orbital becomes, because it looks like in the chart it becomes a little bit lower in energy.
What was the sigma star antibonding orbital actually goes up in energy a little bit. And then what was the sigma bonding orbital goes down in energy. All right, others? Yeah.
So you said the electron density kind of goes to the adjacent hydrogen and then bonding on the top?
Yeah, a little bit of the LUMO is actually on the adjacent beta proton.
How does that happen if they're different wave functions?
Sorry, say that a little bit louder.
How does that happen if they're different wave functions?
How does that happen if they're different wave functions? We have mixed these two separate wave functions together, 2 orbitals in, we get 2 orbitals out. So this is the plus combination down here. You can tell it's the plus combination because the sigma and the sigma star have added together with the same wave function sign. You can tell it's the minus combination here because they've added with opposite wave function sign. Thank you. All right. So the point here, yeah, go ahead.
I guess when you combine 2 orbitals, that's when you form a bond, right?
When you combine 2 orbitals, that's when you form a bond. And in some ways, we've done that a little bit. It's almost like this is still mostly a sigma bonding orbital, but there's a little bit of pi bond character to it. Just a little, yeah, just a little bit. In a way, what we're describing, what I'm trying to show you with orbitals is what you could show with a form of resonance structure that you don't want to know about. What if I, instead of, what if I drew a resonance structure this way? So I'm going to keep all the atoms in the same places, but I'm going to put a plus here and a minus there. I keep everything in the same. These are so-called no-bond resonance structures. You might imagine they're minor contributors to the actual structure. But what it says is that there is partial pi bond character. And that's the same thing that this orbital picture gives us. All right. Consequences of hyperconjugation. Again, the sigma bonding orbital spreads out onto the adjacent alpha carbon. The sigma antibonding orbital spreads out onto the adjacent beta hydrogen. And yeah. Yes? The opposite wave function represented in pink. Well, what I'm showing here, do they not interact with each other? Sort of. What I'm showing you here is basically the same thing as mixing 2 p orbitals together with the same wave function sign to get a pi bond. and then mixing two p orbitals together with opposite wave function sign to get a pi star where there's a node in the middle. That's essentially what we're seeing here. There is a node at that point. Oh, sorry, down here, these two pink parts, probably these two pink ones do oops, shoot, my eraser needs to be smaller. These two pink parts probably do interact. I might have drawn them overlapped like that. I can go back and edit that a little bit later, yeah. Good, others? Yes?
Are there any characteristics that are predictive of hyperconjugation?
Any characteristics that are predictive of hyperconjugation? Could you,
Does every molecule experience this, or no?
does every molecule experience this? Yes. In fact, hyperconjugation is a way you can sort of bridge our valence bond theory picture of bonding with MO theory. It'll get you to the exact same answer. There are a lot of times when hyperconjugation is important, and I will point them out in the future. The reason we're doing this at this time is so that now you can understand that a nucleophile looking at this molecule doesn't just see the sigma star on, oops, that's an eraser, not a laser pointer, doesn't see the sigma star, just see the sigma star on the carbon-bromine bond. It actually sees two things, that LUMO, which is mostly, I feel like we're in The Princess Bride, this is still mostly the carbon-hydrogen, or the carbon-bromine sigma star, but a little bit the carbon-hydrogen bond. And what that means is a nucleophile approaching this molecule is going to have a choice. It can attack that sigma star at two locations. It can attack at the alpha carbon or the beta, the beta hydrogen. All right? And those two choices are going to have distinct consequences that we need to be aware of. Because if you attack, let's see, maybe we'll just redraw so that re-emphasize things. If you attack this LUMO at the alpha carbon, you'll see just what you would expect for a substitution reaction. So I'm drawing now the orbital that we get from hyperconjugation. Oops. This is that minus high energy combination. This is the LUMO that shows us, this is the drawing that shows us that the LUMO is both on the alpha carbon and on the beta hydrogen. So let's show what the consequences of both these things are. If a nucleophile attacks at the alpha carbon, we're going to break the carbon-bromine bond, and we're going to make a substitution product, right? That is sort of how we've described an SN2 reaction in the past. I'm not necessarily sure how to draw this. That's fine. We'll just put the nucleophile here. We'll put the carbon down here to show inversion of stereochemistry if that were a stereocenter. But that's the SN2 reaction, and that's what we get if we attack at the alpha carbon. On the other hand, if we attack the LUMO at the beta hydrogen, we get an entirely different consequence, which, let's see, I guess I need to shrink some things because I want it all to be on the same page. All right, so now let's show the nucleophile attacking, it can be negatively charged, fine. Let's show the nucleophile attacking at the LUMO at the beta hydrogen. What do you predict is going to happen? And maybe to see that, you should sort of remind yourself of the resonance picture of hyperconjugation, where we keep the proton in the same place, but we move the electrons over to form a pi bond, and then we have to put these electrons on the bromine. If you attack the hydrogen, what do you predict is going to happen? Go ahead.
So you're gonna make a double bond?
Right. Then these electrons, it's going to make a double bond. Then these electrons, which were in the carbon-hydrogen bond and were already partially delocalized into that sigma star, we remove the proton, they're going to dump themselves entirely into the sigma star, and then the bond breaks, we form a new pi bond, and then the carbon-bromine bond breaks. And that's called an elimination reaction, because it involves both the nucleophile and the molecule that has our CBr bond. We're going to call this a bimolecular elimination reaction, or E2. But the product of this reaction is going to be, we're going to have a new bond between nucleophile and what used to be the beta hydrogen. We just made a new pi bond between alpha and beta carbons, and then we had a leaving group leave. I should have put the leaving group having left up there. So these are two possibilities that compete with each other. A nucleophile can attack either at the alpha carbon or at the beta hydrogen. If you attack at the beta hydrogen, you break the bond between the beta hydrogen and the beta carbon. The electrons in that bond go to form a new pi bond between alpha and beta carbons. And then you have to break the bond between the alpha carbon and the leaving group. All right. So questions about that, why it happens, what's going on? Yeah?
Isn't it technically more energy for E2 compared to attacking the
Is it more energy to do E2 than SN2? No, in the sense that the LUMO is on both atoms. It's just in both places at once. So a nucleophile could choose to attack one versus the other.
No, there's consequences.
Are there differences? Well, so it's a good question. If they're always competing with each other, if a nucleophile always has to make that choice, are there some sensible ways you can reason which pathway is more reasonable? The answer is yes, and we'll talk about that. Right now, it's enough to know that there are two possibilities that you have to be aware of. What else? Yeah.
So the first one is the substitution?
Right.
Elimination?
Yep, the first one is the bimolecular substitution reaction, and the second one is an elimination reaction. Substitution is the subject of Chapter 7. Elimination is the subject of Chapter 8. The way the text goes is you do substitution reactions and you pretend like elimination doesn't exist. Then you do elimination reactions pretending like substitution doesn't exist. And then at the very end of Chapter 8, there's a whole section which is sort of horrible, where they pull back the curtain and tell you, by the way, all of this was happening all at once. I'm trying to reveal that to you from the beginning so that you're prepared for that. All right, what else? Yes?
Since you said that it still has mostly the sigma bond CBr character,
Yeah.
on the previous slide, does that mean that the substitution reaction happens a lot more often than the elimination?
It's a good question. Since I said that that the LUMO is still mostly the CBr sigma star, does that mean that does that mean that the substitution reaction happens more than the elimination? That is a great question, and we're going to see that the answer to that question is context dependent. We're going to see that there are attributes of the nucleophile. Whoops, that's an eraser, not a laser pointer. There are attributes of the nucleophile that will prefer substitution versus elimination. There are also attributes of your alkyl halide, the thing that has the leaving group, that will, stinking apple and its gestures. I didn't mean to do that. There are also attributes of the alkyl halide that will prefer substitution versus elimination. Okay, so we'll talk about that. We're actually going there right now, but go ahead, yeah. So yeah, our E2 reactions will always have an option to go SN2, same thing with SN2. We're going to discuss what features of the nucleophile make it prefer SN2 versus E2. We're also going to discuss what features of the electrophile make it prefer SN2 versus E2. Okay? Other questions? Yeah.
When the carbon bromine bond's getting broken, is it because it's filling the anti-bonding orbital in the E2 reaction?
Yeah, you can think of it that way. When the carbon bromine bond gets broken, why is that happening? Well, because what before with hyperconjugation was only partial mixing now becomes full-on complete mixing. You remove the carbon hydrogen bond, these electrons you can think of being dumped fully into the sigma star, and then the leaving group leaves. Yeah?
Does the hydrogen on the alpha carbon also experience hyperconjugation?
Does the hydrogen on the alpha carbon, so this one, also experience hyperconjugation? No. In order for hyperconjugation to happen, this is something I didn't say, the bonding orbital and the anti-bonding orbital have to line up parallel to each other. In the same way that when we had two p orbitals forming a pi bond, they had to line up parallel to each other. We talked about how if they line up perpendicular, there's no interaction. Exact same thing with hyperconjugation. If they're not lined up parallel, no deal. And that creates an interesting requirement for the beta proton in an elimination reaction. This is really important. The beta proton must be anti to the leaving group on the alpha carbon. If we were to look down this bond between alpha and beta carbons and draw a Newman projection, here is the alpha carbon that I'm referring to. I'll draw the other hydrogens. Then down here is the leaving group. And notice that the beta proton that gets removed, the alpha carbon's in the back, so you can't see it, is anti to the leaving group. I will now draw the orbital portion of the LUMO that's on the beta carbon. And then in the back, where you can't see it very well, I'm going to draw the orbital portion of the LUMO that's on the alpha carbon. And then here's the other portion of that. So I'm just trying to draw for you the view of the structure to the right in sort of Newman projection format so that you can see that they have to, in order for hyperconjugation to occur, the beta proton has to be anti to the leaving group so that it can line up with the sigma star. Okay? That's a requirement in chapter 8, that arrangement, the beta proton anti to the leaving group, anti but in the same plane, is called anti-periplanar, and it has stereochemical consequences, which we should talk about. In the same way that the SN2 reaction has stereochemical consequences, recall that if the leaving group is at a stereocenter, backside attack gives you inversion of configuration. So too with the E2 reaction, having the requirement to have the leaving group anti to the beta proton has some important stereochemical consequences, which don't appear in the example that I've given you, but I'm going to give you an example where that becomes much clearer. All right, so I'm going to draw for you an alkyl halide. Lovely benzene ring. Let's use this iodide leaving group. And then And then we've got, oh, sorry, I wanted one of those not to be a hydrogen, but to be a methyl group. All right. So I'm going to be generic at this stage about what the nucleophile is. And we're going to draw the products of this reaction that would occur if it were an SN2 reaction or if it were an E2 reaction. In other words, we're going to build in from the beginning our understanding that SN2 and E2 compete because a nucleophile can attack the LUMO either at the alpha carbon to get a substitution product or at the beta hydrogen to get an elimination product. And we're going to draw both of those possibilities. So let's draw here. Let's draw the product from attack at the alpha carbon. In other words, substitution attack. And so what would that look like? Nucleophile attacks at the alpha carbon, that's attacking the sigma star, so the leaving group leaves, right? So what should that product look like? Basically the same thing. Only I'm going to have the nucleophile bonded to the alpha carbon instead of the leaving group, because the leaving group, I minus, left. What should the stereochemistry of the nucleophile be? Should it be a dash or a wedge? Dash, that is correct. You know that's correct because SN2 proceeds via backside attack, giving you inversion of configuration, right? We talked about that last time. You may need to work with a model set to convince yourself that what I've drawn is correct. Now, let's do the same thing, only for the purposes of drawing our mechanism, I'll put that there. Let's show what the product is if we get attack at the beta hydrogen. Before we draw the product, we need to confirm that the beta hydrogen is anti to the leaving group. Is that currently anti to the leaving group? No? Okay. So then what? How would I rearrange things? The other question we want to ask is it possible through rotation around carbon-carbon bonds to get that beta hydrogen anti to the leaving group? So what we're going to do is we're going to keep the benzene ring, the alpha carbon, and the beta carbon all in the plane of the page, but we're going to rotate around the bond between alpha and beta carbons, and we want to do so in a way that gets the beta proton anti to the leaving group. So how am I going to do that? Where does the beta proton need to go? Which of these three positions in the plane of the page, dash or wedge, is the proton going to be anti to the leaving group? Dash, okay? If you don't see that, notice that as we've drawn it here, this benzene ring is anti to this benzene ring. This iodo group is anti to this methyl group, okay? And this proton that is a wedge would be anti to this proton that's a dash that we didn't show, and which I'm going to promptly erase. So we need to rotate around that bond such that the beta proton now occupies the wedge position. So I'm just going to erase these groups. I'm going to keep everything in the same place. If I rotate around the bond, that's going to involve taking that hydrogen that's a wedge and pushing it into the plane of the page so that it's here. Why is that gray? And if that's difficult to see, you're going to need to build a model. Okay, what should be at the wedge now? The CH3, where's that going to go? Remember, I pushed the proton into the page. That's going to cause that CH3 group, which was already in the page, to swing up and now be here, right? So the methyl group goes here, and then the benzene ring goes where the wedge is. I'm going to show you something you can do to abbreviate benzene rings. The abbreviation PH stands for phenyl group, which is what we call a benzene ring when it's attached to something else. It's a lot easier than drawing that, right? Okay. So now, now it might be useful actually to draw the Newman projection just to confirm that the beta proton is anti to the leaving group. So here is that Newman projection. The beta carbon is in front. From our perspective, the CH3 group is oriented straight up. The phenyl group would be out to our left, and the beta proton is to our right. This is us. That's not much of a nose. Oh well. Okay. Anti to the CH3 group is the benzene ring in the back. Coming out towards our left would be the iodide, which is the leaving group, and then here's the other hydrogen. Okay. You agree so far? We're not going to draw the hyperconjugation orbitals, but we know that that can happen now that the beta hydrogen is anti to the leaving group. Now let's draw the elimination reaction. Nucleophile with a negative charge is going to remove the beta proton. Electrons kick down and leaving group leaves. We can draw that from this perspective too. And leaving group leaves. Now notice that as we remove this hydrogen and as the leaving group leaves, a new pi bond is going to form between the beta carbon in the front and the alpha carbon in the back. And notice that these two benzene rings were on the same side of the molecule, gauche to each other. And as that pi bond forms, they're going to stay on the same side of the molecule. So the product from this elimination reaction is the one that has the two benzene rings cis to each other. Okay? Notably, not the other stereoisomer. This is what I meant when I said that the E2 reaction has stereochemical requirements. If you had drawn me the other stereoisomer, the one where the phenyl groups are trans to each other, you would have communicated to me that you do not know that the E2 reaction requires the beta proton to be anti to the leaving group. All right? So that requirement has stereochemical consequences, and that's really important. Questions about that? That seems obvious here. It's not going to seem obvious when you don't have the answer in front of you, so you're going to want to practice that. There's some problems in the text, in the practice exam, in the study guide that are going to push you on that. I deliberately chose an example where there was only one kind of beta proton. Had this been another beta proton instead of a methyl group, we would have had a different outcome. And had there been another carbon over here with other beta protons, we likely would have had different outcomes. We're going to go there and we're going to deal with all of that, but for now, being aware that the E2 reaction has stereochemical consequences and that it requires the beta proton to be anti to the leaving group is going to be good enough. Yeah?
Can you review how we know that, how do you know that they're cis to each other just from they have to be anti?
The two things that have to be anti are the beta proton and the leaving group. That determines everything else. If in the conformation where the beta proton is anti to the leaving group, stuff that's gauche to each other in that conformation has to be cis to each other in the final alkene. Because in order for these, if it were different, or let's see, what's a better way of saying that? Another way of looking at that is, again, when you have the beta proton anti to the leaving group, pay attention to the other groups that are anti to each other. Phenyl group anti to a methyl group, that also has to be true in the final alkene. Phenyl group anti to a methyl group. Yeah. Because there's no, as the leaving group's leaving and the beta proton's being removed, there's no time for rotation around that bond anymore. Yeah. Okay, yes?
So just to clarify, beta proton is called that because it's attached to the beta carbon?
That's right. The beta proton is called that because it's attached to the beta carbon. Saw another hand? Yeah.
Can you explain why there's a double bond now in our product?
There's a double bond in the product because we remove the proton. The electrons in that carbon-hydrogen bond go to form the new pi bond, and the leaving group leaves. So that's what an elimination reaction is. Yeah. Other hand? No, miss somebody? No? Okay. All right. So now let's talk about what helps. Let's talk about the features that promote substitution or elimination relative to each other. Okay? So to do this, we need to talk about the different kinds of alkyl halides. So, or different kinds of situations where you have a leaving group. This is called a primary leaving group. This is called a secondary leaving group. LG stands for leaving group. The little degree sign makes that 2 secondary instead of 2. Secondary leaving group. And then this is a tertiary leaving group. It turns out that SN2 is fast for primary leaving groups. It is moderate for secondary leaving groups, and it is impossibly slow for tertiary leaving groups. In other words, if the leaving group is tertiary, there is no SN2. The reason for that has to do with sterics. If, and we will look at a space-filling model, but you can imagine that the more non-hydrogen things you have, the more difficult it is for the nucleophile to access the sigma star. We're going to see similarly, well, in sort of an inverse way, that the E2 reaction is fast for tertiary alkyl halides. It's moderate for secondary alkyl halides, and it is slow for primary alkyl halides. So you can see that you can make some decent decisions here now based on alkyl halide structure. If it's a tertiary alkyl halide, and you have a competition between SN2 and E2, E2 is going to win because SN2 is impossibly slow. Similarly, if you have a primary alkyl halide and it's a competition between SN2 and E2, SN2 is going to win because E2 is too slow. All right, we'll pause there. See you tomorrow for Real Wednesday.